As we continue this example problem, we are going to figure out how accurate of a predictor this exponentially smooth forecast is for future days using three factors: the mean square error, the mean absolute deviation, and the mean absolute percentage error, realizing that for all of them, the smaller this deviation, this error is that we have, the better off we are. To do this, we need to fill in the Excel formulas that are provided over here. We already used the first one to figure out what our y hat was. So let's move on to the mean square error, and that is equal to the sum squared of the residual range divided by how many residuals we have. Well, that means we got to find the residual that we have. And the residual, as our formula up here shows us, is just y, the actual number of calls, minus y hat, the number that our model predicted. So for day 2, when we actually had 292 calls, we're going to subtract out the 309 that our model predicted, and we see that the actual amount that we observed was 17 less than what our model would have predicted. And with that, I can fill handle to fill in all the rest of the spots. We get the residual for each and every day within our 21-day period. So now to find my mean square error, I can just fill in formula. This is equal to the sum squared, so sum SQ, of the residual range, which we just calculated right here. It's going to be cells D3 to D22. Close that parenthesis, divided by how many there are, which we know is 21, but I could be thorough and just divide it by the count A function of that same range, D3 to D22. And that comes out to 217.16. The next measure of goodness of fit that we're going to use is the mean absolute deviation. We have the formula for the mean absolute deviation in our formula bar. It is equal to the sum of the absolute value of our residual range divided by how many residuals we have in our information, which I misspoke earlier, should be 20 since we don't have one for day 1 because it's the same number. We are going to, in this case, fill in our mean absolute deviations formula as it's equal to the sum, open a parenthesis, of the absolute value, so ABS, open another parenthesis, highlight our residual range, which is cells D3 to D22, close that parenthesis, divided by count A of that same residual range, cells D3 to D22, and our formula should look like that. And when I put that in right now, the mean absolute deviation is going to be, it wants to go through, 12.91. And lastly, for the last measure of goodness of fit that we have, we're going to find the mean absolute percentage error. Well, to do that, I got to first find the absolute percentage error of each residual that we have. So the absolute percentage error, for example, over here in our first spot that we have available in cell E3, is going to be equal to the absolute value, so I'm going to open a parenthesis right now, of our first residual, which was in cell D3, that negative 17, close that parenthesis, divided by the actual value that we had during that period, 292. So what we're saying here is that was 17 off of the 292 that we had. Close that parenthesis and multiply it by 100. That 17 that we missed by on day 2, according to our prediction, ended up being 5.82% off from the actual number of calls that we received. I can go through and I can fill in the rest of this column by double-clicking the fill handle, and there we go. We have the absolute percentage error for each day. We see what percent of our actual calls our prediction was off by. And now I can find the mean absolute percentage error by taking the sum of the absolute percentage error range, which is everything we just calculated in cells E3 to E22, and dividing it by how many points we have that absolute percentage error for, which is the same exact range in cells E3 to E22, which would be those 20 points that we have. And that comes out to be 4.32. Well, how good are those numbers? And that's something you can't answer from what we have right now because we don't have anything to compare it to. But we want to know that these are all measures of goodness of fit. And the smaller that these numbers come out to be, the less error there was, the less deviation there was, in our example. Why would you want that information? Well, there's no rule that says that alpha has to be 0.20. This is a trial and error thing. You can play around with what your alpha is over and over and over again until you find the alpha based upon your existing information that gives you the best goodness of fit by giving you the lowest mean square error, mean absolute deviation, and mean absolute percentage error.